Okay, section 8.2, operations with matrices. So, matrices represent quantitative data that can be counted. So, of course, it naturally follows that matrices are composed of quantifiable data. They can therefore be quantified with each other through operations addition. Of course, then also subtraction, you're just adding a negative amount of the same thing. And then also, we're going to look at matrix multiplication, which is a little trickier. The addition, really straightforward, okay? Matrices are denoted usually by an uppercase letter, and then the individual data entries are lowercase, with the subscript telling you which row and which column. So lowercase a sub ij or lowercase b sub ij, so on. So when you want to find each data entry within a matrix corresponding with the subscripts, the row, and then the column. So a sub 1, 1 is the first row, first column. That is 2. A sub 2, 1, second row, first column. That's -3. And then, of course, -1 and 0. Matrix addition, again, really straightforward. A given matrix had an order of m by n, so many rows by so many columns. Now if you have two matrices, matrix A, matrix B, they're both of order m by n, so they're the same order. The addition is just the individual corresponding entries added together. So we look at example A. Both matrices are order 2 by 2. So to add them together, just add the corresponding entries. The entries from the first row and first column, -1 and 1, is 0. Entries from the first row, second column, 2 and 3, 5. From the second row, first column, 0, -1, -1. Second row, second column, 1 and 2. That's 3. And remember, addition or subtraction, of course, they have to be the same order, okay? So look at the rest of those. Check your answers with my complete notes online. Scalar multiplication. If you have C, some constant, times matrix A, that means C applies to every data entry in matrix A. This is really just, you're familiar with this, as the distributive property. Whatever numbers are in front, distribute that number to each entry. So addition, scalar multiplication, pretty straightforward. Matrix multiplication is a little trickier. You got to do some preliminary work to organize the operation and then carry it out. So for the product to be defined, the number of columns, thus up and down, in the first matrix must equal the number of rows in the second matrix. So matrix multiplication is not necessarily commutative. So if you have a matrix that works, a matrix multiplication that works, matrix A is m by n. Matrix B, the rows have to equal the columns from the first. So n by p. What's inside the n's must be equal. Then what's outside, the m rows from the first, the p columns from the second, that will be the order of your answer. So your answer is a B with order m by p. So I strongly encourage you to set this up every problem you do. So let's look at that. We have matrix A here is a 2 by 3. Matrix B here is a 2 by 2. So A times B. Now A is a 2 by 3. B is a, I'm saying not 2 by 3. I'm sorry. 3 by 2. Go down, then over. I'm setting up and like, wait a minute, those aren't equal. I must have done something wrong. Now I'm talking, getting more things wrong. Okay. So, inside the 2's, those are equal. Good deal. So we can multiply. Matrix multiplication is not always commutative. If you want to do matrix B times matrix A, wouldn't that work? You switch it around, you'd have 2 and 3 not equal. And then the outside, that's going to be the order of your answer. So there's a little predictive quality to this. So we're going to get matrix AB. And that will have an order of 3 by 2. 3 down, 2 over. Now when we do this, okay, there's a little bit of movement to this process, almost like a dance. You do this, then that, and then movement happens. So when you multiply, you kind of go right to left. You take a column from the second matrix and you kind of rotate it 90 degrees counterclockwise up. So -3 rotates over, -4 rotates up and over. And then these values, they're going to filter down through. And they're going to multiply to every entry, and then those will add together. So we have matrix AB, and that's going to equal -1, -1, 4, and 5. So you see I just copied the first column from A down here to my answer, and -3 is going to filter to each of those values and multiply. So -3, -3, -3. And then your second column, 3, -2, 0. And then that -4 up on top is going to filter down. So -4 is going to filter down, multiply by every term. And then these two columns are going to add together. Okay? So the column from the second matrix gonna rotate 90 degrees counterclockwise up, and then filter down through matrix A. And once you do this setup, you just repeat it with the next column. And however many columns you have, you do it that many times. So the 2 rotates up 90 degrees counterclockwise. The 1 rotates up 90 degrees counterclockwise. It's a horrible looking one, wow. Not great, but better. And then the 2's gonna filter down. The 1's gonna filter down also. So I'm gonna copy here, so -1, 4, and 5. Which is the first column from matrix A. And then every single one of those entries gets a 2 filtered to it. Then the second column, 3, -2, 0. Each of those is gonna get a 1 filtered to it. Then those results added together. So you see my result is going to be a 3x2 matrix. 3 rows, 2 columns. So now I'm going to do a bunch of mental math. So -3, -1 and -3 plus 3, -4. So 3 and -12. -9 and -12 and 8, -4, -15 is 0, -15. And now -2 and 3, -1, boy, lots of negatives. 8 and 8, hey, +6, good for us. I don't know why, but okay. And 10 is 0, is 10. And we see our result is a 3x2 matrix. Go ahead, do the rest of the examples, check your work with my complete notes online.